All right, hello everyone. Thanks for joining today. Thanks for attending our episode 20 of Warsaw Quantum Computing Group. Our lecturer today is Michał Steinhuth from Zapata Computing Quantum Open Source Foundation. I guess that Michał will also tell you a bit more about himself. And he will give a lecture titled Variational Quantum Algorithms. How do they work? A very interesting title. The meeting is recorded, and after the meeting, we'll prepare a video and publish it on our YouTube channel. If you have any questions, you can ask your questions on the chat, and later, after the lecture, we can ask your questions during the Q&A session. Michał also told that there will be opportunity to ask some questions during short breaks. Yeah, I think we can start. So Michał, the floor or the Zoom is yours. So let's start sharing your screen now. I'm stopping sharing mine.
Okay. Great. Hello, everyone. I'm really happy to be here. Thank you, Paweł, for inviting me. So can everyone see my screen?
Yep, we can see your screen now.
Okay, great. So, hello, my name is Michał. And today I would like to tell you a little bit about variational quantum algorithms and the reason behind, their working. So the plan is that I'll quickly tell you about myself and introduce what are variational quantum algorithms. Then I will go through two arguably most important variational algorithms of the past, decade. So VQE and QAOA, then explain a little bit about what are some challenges of the noisy intermediate scale quantum computers, and at the end, try to generalize the structure of VQAs a little bit. So there will be, as Paweł said, probably after VQE and QAOA, I will make some short breaks to make sure we are all on the same page. So, and also VQE and QAOA are heavily based on two of the blog posts I've written. So if you get lost, don't worry, you can always rewatch the recording, or you can just check out the blog post and see what I meant by that. So about me, so I work at Zapata Computing as a quantum software engineer, where I helping to build Orchestra, which is our platform for doing computations with quantum computers. I'm implementing various algorithms, and I'm also helping with various research projects from time to time. Apart from that, I'm one of the members of the Quantum Open Source Foundation, where I'm running a mentorship program that has recently finished. So you can find some projects that we did in the mentorship program on the QOSF website. I'm also involved in Q4Climate, which is an initiative which focuses on finding ways for quantum computers to help tackling climate challenge. We are in a little bit in a silent mode for now, but I hope we'll have something to say in a couple of months, say more. And also I have a blog called Musty Thoughts, where I write about quantum computing and other stuff. I highly recommend you to check it out. So that's it. Let's get to the real thing. So what is a variational quantum algorithm? So variational quantum algorithm is basically an algorithm which uses hybrid approach. So some calculations are done on a classical computer, some are done on a quantum computer. And usually VQAs work like this. So we have some qubit Hamiltonian, which describes the problem that we want to solve. We have some ansatz, more on what ansatz is later on. But basically some quantum circuit which is parameterized, and we have some parameters. So we put that in a run this circuit on a quantum computer. We measure the quantum state, and based on that, we can evaluate energy. So we get some, some number basically, which we can then pass to a classical optimizer alongside with the parameters. So the classical optimizer says, okay, so this is my current value of the cost function. These are the parameters. I would like to find some new better parameters. So it calculates new set of parameters, and then we evaluate the state of the circuit again. We get new energy. We pass it again to classical optimizer, and optimizer tries to figure out new set of parameters. And we repeat it until there's some convergence or we obtain some target value. So that's basically how the variational quantum algorithm works. There are three, I would say, most significant types of VQAs. So this is VQE, so variational quantum eigensolver, QAOA, quantum approximate optimization algorithm, and QNN, which is like quantum neural networks. There are some others, but I would say these three probably cover most of the interesting cases. And I will today focus on the first two. So I hope you will, at the end, I would rather not to kind of talk about VQAs in some abstract manner. We'll get to that later, but I will show you concrete examples of VQE and QAOA. So I hope you will have much better understanding of, what these are, and learn what variational quantum algorithms are on these two examples. So the first one that we will be talking about is variational quantum eigensolver. So variational quantum eigensolver, it uses variational principle to calculate ground state energy of the system, right? So I will quickly go through some important concepts that we'll probably be using a lot during this presentation. This is kind of basic quantum mechanical stuff. So if you are familiar, please bear with me for a moment. If you are not, we are not going into very deep details on what these actually mean. So what's a Hamiltonian? Hamiltonian is basically an operator that describes the energy of the system. And since we are in quantum mechanical realm, we know that energy is discretized, right? So we can only have some discrete values of energy. And every state has associated energy. So in this case, Hamiltonian describes the energy of the system, and eigenstates are those states that have this discretized value of energy. So each eigenstate has some state energy, right? And the ground state is the state which has lowest energy of all the states that we kind of are dealing with, right? And it's important to know that by definition, energy of any state is greater or equal the energy of the ground state, right? Because, ground state has the lowest possible energy. So how does this links to the variational principle? So variational principle is a method which says that if we have some state and we evaluate its energy, we can, the state which is in some way parameterized. So if we can find some energy, we have a state with some energy, we always know that the energy is greater or equal ground state energy. So variational principle says that we can estimate the value of the ground state energy by trying to find state which gives us the lowest energy that we can find. So it's estimating by basically finding the upper bound of the energy. And the thing that we care here about is the ground state energy. So why do we care about ground state energy? For two reasons: that it's useful, and it's something that's pretty hard to obtain with classical computing. Why it's useful? So I'm not a chemist, and this is kind of my high-level understanding, but ground state energy is often used as input for other calculations in chemistry. And if you are familiar with machine learning, there is the good rule in machine learning, which is called garbage in, garbage out. So if you provide like low quality input data, you cannot expect high quality results. And the same is true here, because if we provide ground state energy, which is very inaccurate, our final calculations will also be very inaccurate, right? So the better estimation, the better value of the ground state energy we can get, the better we can, the better is the performance of our overall algorithm that calculates some properties of the chemical reaction of a material or whatever else. So we don't care about, usually ground state energy as itself doesn't have like real kind of practical implications. It's the stuff that we can calculate when we know ground state energy well. And the other thing is that it's hard to get with classical computing due to the fact that if you have a molecule and you care about electronic configuration, so we have a lot of electrons, they can be, have different spins, be in different kind of excitations in different orbitals. So you really, like, the number of possibilities grows exponentially, and it's really intractable to check all of them with a classical computing. So quantum computer helps here and allows us to simulate a quantum mechanical system on a quantum computer, which seems like a natural fit. So okay, so in order to make use of variational principle, we need basically three things. So the one thing is we need some method of encoding the problem so that we can translate it to the language that basically a quantum circuit. We need some method for preparing the parameterizable state, because that's something that we need for variational principle. And we also need some method for finding a good set of parameters. So I will go through how do we solve each of these issues in the following slides. So one thing that's worth always remembering are Pauli matrices. So Pauli matrices are like kind of very basic matrices, and we use them in quantum computing a lot. And they are basically here sigma x, sigma y, sigma z, and they correspond to x, y, z gates in a quantum computer. And they are important because in a lot of cases in quantum chemistry, we can decompose Hamiltonian in such way that it's a sum, like it's a tensor product of sum of tensor products of Pauli matrices. So Pauli matrices are basically the building blocks for doing VQE. A good example of how to do that, I've gave here the link, and also I will give link to the whole presentation so you can explore some other sources that I put here. But this is a very good tutorial which explains how to map a Hamiltonian from kind of quantum chemistry world into quantum computing world. This is for the Fermi-Hubbard model, but it works well in general. So we need to express our Hamiltonian in the terms of Pauli matrices, and it can look something like this. So this is a simple example of the hydrogen molecule H2, and this is how a molecule, how the Hamiltonian might look like. So as you can see, we have like different terms here. So we have constant term, this is like identity. We have Z terms, so these are like Z acting on the 0 qubit, Z acting on the 1 qubit, on the second and the third qubit, right? So, and like with some coefficients. And it's not really important, like where how this mapping exactly happened. So I won't be getting into it right now. What's important is to see that, well, we have those simple terms of like, you know, single operators, and then we have tensor products. So it's z0 times z1, right? So this is acting on 2 qubits. And then we also have those terms with x and y acting on all the 4 qubits in like different combinations. So Hamiltonians that we deal with, you know, may look something like this, and it might not be easy to actually calculate all the states, all the eigenstates, and finding the ground state with the classical computer. In this case, it's easy because, you know, this is 4-qubit system, but if we get into much bigger system, it gets harder and harder. So how do we, so that's like the first part. So there is a way of mapping the problem, the structure of the molecule, into a Hamiltonian that we can use for our calculations. The second part was, how do we come up with a parameterizable circuit that we can use? So here ansatz comes to the stage. So ansatz in quantum computing, ansatz is basically, we can think about it as a parameterizable circuit, right? So in this picture, you can see like a very simple kind of set of states, right? Which are all described, can be described by a simple ansatz. So the ansatz that will produce these states is just like a single RY gate, right? Parameterizable by some angle. So for the angle of 0, we are here. For angle of pi, we are here. And for all the intermediate angles, we are, you know, somewhere here, right? So with this ansatz, we can explore kind of this like circle on the Bloch sphere. And actually, there is a useful concept which is called expressibility, which basically means how many states in the whole space of all these possible states we can explore with given ansatz. So as an example, an idle circuit can only explore, you know, a 0 state because it doesn't do anything, right? For a circuit which has a single RZ rotation, we can only explore the states that lie on this circle, right? If we add another rotation, we can actually explore the whole Bloch sphere. And with arbitrary unitary, you know, we also can explore the whole Bloch sphere. And it's important to have ansatzes which have higher expressibility, because then we can actually create more states, and, you know, it would be it's like more probable that a ground state of the system actually lies somewhere within the reach of given ansatz. It's harder to visualize for multi-qubit systems because we don't have like multi-dimensional Bloch sphere, but it really gets like an interesting problem of telling like how expressible given ansatz is and so on. And I recommend this paper that I linked here. It explores it in much more details. So a metaphor that I like to explain like how the like reaching different states, what does it mean, and what are some issues with the ansatz, is a metaphor of a robot. So this is a simple SCARA robot which has a rotating arm, right? So, you know, it has an arm which rotates around this axis, and it has this holder. So we can put a pen in here, right? And if we try to all possible angles that the robot can rotate, we'll get kind of this green line, right? So this is a set of all the points on the huge white piece of paper that this robot can reach. So what can we do to actually increase the possible space of achievable states? we can add another arm, right? So at the end of the first arm, we can add the second arm, and then we increase a lot the state that's reachable for the robot, right? Now we can basically cover all that. So what can we do next? Well, we can add, you know, to increase the reach of the robot even more, we can add more and more arms. But actually, when you think about, you know, it's nice to think about it in abstraction, but when you think about kind of more realistic case, adding more and more arms might actually not be that good idea for several reasons. So one of the reasons is that without one arm, you have one parameter. With 2 arms, you have 2 parameters. But with 20 arms, you have 20 parameters. And controlling all the 20 parameters at the same time might be really tricky. The other thing is that actually, perhaps this arm don't have like the full spectrum of angles they can reach. Perhaps they have the angles they can move are discrete, right? So then it also like limits the number of states we can reach. Another thing is that arms can also have like their own errors, in the sense that we might not be able to precisely say that move, you know, to angle of 90 degrees. But because there will be error, and it might turn out that it's not 90 degrees, it's 90.01 or 89.97 degrees. And the more arms you have, the more these errors, you know, kind of, they multiply with each arm. So the system is less and less reliable. And these are basically the very similar problems as the ones that we have with the ansatz. So how to say that given ansatz is a good ansatz? So it should have high enough expressibility. I said enough because you can also imagine cases that you know that the ground state, for example, you know, is restricted to like some space, because you might have that knowledge from elsewhere. So then it doesn't make sense for the ansatz to cover the whole state of the whole space of possible states. It's enough for the ansatz to cover just the space where you know the solution lies, right? And the ansatz should have low number of parameters. I mean, the lower the better, because it's easier to control, but again, you need it to balance it with the expressibility. It also needs, it's preferable if the ansatz has lower depth. We are in the NISQ era, our quantum gates are, you know, noisy and like imperfect. So the smaller the number of the gates that we use, the better, because there's less room for error. And also it would be nice if the ansatz was kind of hardware aware, in the sense that there is, if again, like this comes from the fact that we are in the NISQ era, and for example, some ansatzes might look very well in theory, but in practice, they, for example, use some gates that are very hard to implement in the real hardware. So if we want to get some real results with, you know, our ansatz, we need to take into account, for example, what gates are available on the given hardware, or what's the connectivity of the chip. Okay, but that's it about ansatz. And now we should think, you know, okay, we have this ansatz, we have prepared the quantum state, but actually we don't care that much about the state, we care about the energy of the state, right? So how do we get the energy? So in order to get the energy, we need to calculate like the expectation value of the Hamiltonian. And well, this is this nice equation here. But you know, how do you do that on a quantum computer? That's like, I would say it definitely, it wasn't obvious for me at the beginning. So, because like quantum computers are like, well, okay, sorry. One problem is, for example, that we can only perform measurements in the Z basis, right? So if you take a look at the Bloch sphere, that's where the 0 and 1 live. But how do you deal with a case where you have how do you deal with the case where you have, for example, x and y terms? Or how do you deal with the case where you have actually just like tensor product, right? No, this one is easy because it's constant term. No matter what your circuit is, the energy of this identity term is always the same. In this case, this is also pretty simple because we have just one qubit. So we take our ansatz, we run it, and then we measure what was the value of qubit 0. And Pauli matrices has this nice property that they are 2x2 matrix, so they have 2 eigenvectors. In case of Z matrix, one is 0, the other is 1, and there is eigenvalue, so like energy associated with each of these, and it's 1 for the state 0 and -1 for state 1. So if we measure the qubit 0 and we measure like 0, right, we know that the associated energy is 1. If we measure 1, we know associated energy is -1. So we can run the circuit, measure it many times, see what's the energy that we got, multiply it by constant, and voila. We do the same for all these. Then, in this case, you actually need to measure 2 qubits simultaneously, and this will give you, multiply the energy that you got, energies that you got, and this will also give you the result. But the trick is with this x and y, because, as I said, we can measure in z basis, but we cannot really measure in x and y basis, right? So how do we deal with this? Well, we need to add some rotations at the end of the circuit. So the red, like light red and dark red, are 0 and 1 state. And let's say you want to measure the green state, right? So you measure this green state, and if you measure it, you will get either 0 or you get 1. So if you measure it like 1,000 times, you will probably get around 500 of each. So we can say, okay, I know that this seems like equal superposition, so this seems to be this state. But actually, why not this state or like any other state on the equator, right? You cannot with measuring in the z basis, so either 0 or 1, you cannot distinguish between all these states. So there is a simple trick that we do, which is we take the whole circuit that we have, like the ansatz, and then if you want to measure the x term, we just add a rotation around y-axis by 90 degrees, by pi/2, right? So then, after such operation, this state, light green, becomes the light green here, right? Becomes 1, and the dark green becomes 0. So now, suddenly, even though we measure still measure in the z basis, we kind of rotated our whole state by 90 degrees. So we know like whether we can distinguish between the state that was here or here on the equator. And that's basically how like in VQE, how we evaluate the energy. And then the last piece is classical optimization. So classical optimization requires classical computer. And basically in VQE, there's just one thing that a QPU, so quantum processing unit, does. So given a set of parameters, it returns us a set of measurements, right? And basically that's it. Then what classical computer does, it takes these measurements and calculates the value of the energy. Then it performs, once it has the energy, it performs some optimization procedure to find new set of parameters, right? Calculate these parameters. Then when we repeat it, a couple of times, at the end of each iteration, we need to check whether we actually reached minimum or some convergence or not. And also it for example, keeps tracks of how many iterations we've done so far, and perhaps, even though we have not reached anywhere, it's been 10,000 iterations and we should stop. So these are just like a couple of things that classical computer does in this, but I guess these are kind of most important. Okay, so it might be a little bit, what I was talking about might have been a little bit abstract. So let's go through a very simple example of a very simple ansatz, which is a single RY rotation, right? Parameterizable by some angle theta. So we have this Hamiltonian that we would like to know what's the energy of. So it's 1 qubit system. So I drop the indices, right? So it's 2z plus x plus y plus identity. So we can actually write that, okay, so this Hamiltonian consists of like 3 different Hamiltonians, right? H1, H2, H3. And the total energy of the system consists of like the sum of the energies associated with these Hamiltonians. It's really, really kind of nice that we can, we can treat all of them separately. And the state psi, which we have, is just a state described by this rotation by the angle theta. Okay, why there are 2 circuits in here actually? Well, the first circuit is kind of just the ansatz and the measurement, but this circuit is the one that we'll use for measuring z. But as I mentioned, for measuring x, we actually need to rotate our state by pi over 2. So we have another ry rotation here. So this one is parameterizable theta, this one is parameterizable by p over 2, and then we measure. And we don't need any circuit for identity term because it's always going to be 1. Okay, so let's see. If we have theta equal to 0, we are, on the state 0, right? So when we measure the energy for the z, we get 1. Then we multiply this 1 by 2 because we have coefficient of 2. So the first energy is 2. Well, for the x state, so the ansatz produces this state which reaches like 0. Then we rotate it by p over 2. So from here we get 2 on the equator, right? So when we start measuring it and we do infinite number of measurements, we actually get the same number of zeros and ones, right? So one has energy +1, the other has energy of -1, so the average is 0. So we get 0 from this. And then the identity term is constant, so we get 1. And similarly, for the theta equal to pi, we are in the 1 state. So if we measure it, well, we get -1 multiplied by 2, so we have -2. Then similarly for the x operator, we are on the equator, so we get 0. And for identity, also nothing changes. And for various values of theta, we can get various energies. And here you can see how it changes with theta, right? So the first term, so the 2z varies from 2 to -2. The second term varies from 0 to -1 to 1, right? And then the third one is always constant. So if we add all of them, we actually get a curve that looks like this, and we can find the minimum. It's actually not pi, it's like somewhere here, right? And what I'm not showing to you right now is how to kind of use the classical optimization loop here to go through all the states. On this picture, you see that I simply checked kind of all the values, all the possible values, and draw the curve. But we could use some simple gradient descent or something like this to actually find it without going through all possible values. So okay, so that's it regarding VQE. So I would like to ask if there is anything that's super confusing. Okay, I see Wojtek has a good question. If the ground state of a system is degenerate, does it help variational quantum algorithms? Can cause some troubles, or is it a marginal case not encountered in practice? So honestly, I think it doesn't really matter, because in the end, the goal of the algorithm is to find the ground state energy, right? So if you have the degenerate ground state, then kind of both of the kind of ground state that you have can have the same energy. So no matter in which of them you end up being, you still get the same value. So this is actually a case in QAOA, because in QAOA often like the solution might be symmetrical, and it's not something that that's like really a problem. Okay. So the other question is, okay, so does the low depth affect the accuracy? So basically, the lower the depth of the ansatz is, the kind of more resistant it is to the noise, right? Because you perform smaller number of imperfect operations. But at the same time, that's true that with just one rotation, you can reach only that many states, right? So you need more and more gates to be able to create kind of more elaborate quantum states. So there is this like fine balance between actually the depth of the circuit and the expressibility of the circuit. Like in principle, the perfect ansatz in some sense would be kind of the layer of all the possible rotations, and then all like C naughts between all the possible qubits, because this will give you will allow you to cover that whole space, but then the noise will kill it very fast. So this is like balancing act. What does a qubit represent here? Is it the guess eigenfunction of the Hamiltonian? So what qubit represents in here is kind of tricky, and I don't want to go into like too many details. So I really recommend this this tutorial. It shows you how to map the Hamiltonian described as the sum of annihilation and creation operators into actual like qubit Hamiltonian. How about using quantum natural descent? I mean, that's kind of more advanced, so we might get there to the end. Say if the ground state is 0 and the first state higher that the ground state is 1, and if these are degenerate, then there would be an ease movement of qubit. Okay, so Devanshi, I don't think I get this question really, but I think we can get to that at the end of the talk. And the next question, okay, the good question from Sandeep. Okay, I will just get here good example. Good questions from Sandeep. How to form Hamiltonian in terms of Pauli matrices? Well, there is a method for doing that. There are like a couple of methods. So if you ever heard about Jordan-Wigner transformation or Bravik-Kitaev, that's basically the way of mapping it. As I said, like read that in the tutorial. I recommended it. How does one take an optimization problem? I will cover that in the section about QAOA. Why is measurement only possible in Z bases? It's kind of, I mean, there's probably some really good fundamental reason that I'm not able to tell you now. If anyone can answer this question in more detail on the chat, feel free. Basically, that's how kind of hardware is built, right? It's hard enough to build quantum computer, so we decided to measure everything in Z bases. Perhaps measurement in other bases are possible. I'm not sure if they are actually. That's like the way, definitely the way it was easiest to build. Okay, so that's it for the question for now. And I will get into QAOA. Before I do that, give me just like 30 seconds. I will grab some water and we'll be right back.
Okay, let's wait for Michał. And in the meanwhile, I will just remind that if you have any questions, you can just write down your questions on our chat, and later Michał will try to answer.
Yeah. Okay, so I'm back, and let's go into QAOA. Okay, so QAOA is an algorithm which allows us to solve combinatorial optimization problems using quantum computer. But why do we care about combinatorial optimization problems? Well, because they are everywhere. In like, no matter which industry you look into, whether that's like airlines, it's energy, it's like production, manufacturing, computers, you will find some combinatorial optimizations problems there, and they're like everywhere, and they're pretty hard to solve. So that's why we care. So the combinatorial optimization problem we'll be talking about today is a MaxCut. You know, there are some other COPs that are more popular, like traveling salesman, but actually MaxCut is kind of the one that was used in the original QAOA paper, and that's the one that's like mostly used in the literature, so it's useful to understand how it works. So MaxCut is a problem where we have a graph and we want to divide nodes into two groups in such way that the sum of the weights of the edges between the groups are like is maximized. So I will give you kind of a real life example. So imagine there's a classroom and there are students, and the students are passing notes between each other. And teacher knows very well which pairs of students are passing how many notes. And the class will move to a new class. But in this new class, there is like this huge gap at the, in the middle of the class. So the question is, that teachers want to solve, teachers want to minimize the number of the letters that are passed, right? And teacher can put students either on the left or right side of the gap. So the students won't be able to pass notes through the gap. So basically, she wants to find such placement of the students that those that are passing most notes are sitting on the opposite sides of the class. So let's see how it looks like in this graph. So in this graph, we can say that we want to color the nodes. So there will be like green and blue. So if we color this as blue and all the others as green, the like value of such solution will be 6, because 5 plus 1 is 6. If we color these two as blue and the rest is green, the value of such solution is, well, 1 plus 7 plus 4, right? Because these are the edges that go between the groups. So it's 12. The optimal solution to this problem looks like this, right? So the value of this is 19. And yeah, that's basically the MaxCut problem. Okay, now QAOA. So there are a couple of concepts that are pretty important for QAOA, and I don't go into too much details for each of them, but I think they're important to. It's important to understand them in order to really understand why even anyone bothered about creating QAOA. So let's start. So adiabatic quantum computing is this concept that says, it is based on the, I think it's called adiabatic principle or something like this. So that if you start from some Hamiltonian, which is H0, and you have some other Hamiltonian, which is HP, and you very, very slowly kind of change your system from H0 to HP, which is denoted by this linear combination for the time capital T, then if you start from a ground state of this Hamiltonian and you do this properly, sufficiently slow, then you will always be in the ground state of this Hamiltonian, right? So the trick is that this allows you to go from the ground state of this H0, which is something very easy and something that you'd know solution for, so you can prepare your initial state in the ground state of this, then slowly evolve it over time, so that in the end you are in the ground state of this Hamiltonian, which might be super complicated, and basically have the solution to your problem. Well, there are some issues with this approach. I mean, it looks great, but the problem is that first you need your quantum system to be really well isolated from the outside world, because if there is anything that kind of influences the state, then it might move you outside from the ground state, and then you will end up in some state which is not ground state. So that like kind of kills the whole purpose. The second thing is that well, you need to do it sufficiently slow, and the problem is that basically the time that you need to do that grows as kind of the problem gets harder and harder, right? So if you take like a simple Hamiltonian like this, the final Hamiltonian, then you can probably do it like in pretty short time and you will be okay. But if you have very kind of Hamiltonian for which finding the optimal value is like the ground state energy is very hard, you will have to run it for a very long time. And also there are some issues with implementing adiabatic quantum computing on universal gate-based quantum computers, so the ones with circuits and gates. I mean, it's doable, but it requires a lot of qubits that we don't have today, so it probably won't be feasible for quite a long time. Okay, so that was the first concept. The second concept is something we call Ising models. So imagine a system where we have like a chain of electrons, and these electrons can have either spin up or spin down. Well, in case, and they interact with like their nearest neighbors. So there are two cases. So in one case, they interact in a way that they want to be aligned. They have the same spin as their neighbor, right? And then the solution of such problem is either all up or all down. Or there is this other case where actually they want to be different, right? So then the optimal solution is like up, down, up, down, up, down, up, down. So this is like pretty simple linear case, but what's nice about it is that you can describe such system using only Z operators, right? So the Ising Hamiltonian, so the Hamiltonian describing such system consists only of Z operators, which has some nice properties. And furthermore, if we scale it to, we can scale it to like two-dimensional grid, and then actually this problem gets pretty complicated because you have more nearest neighbors, and it's not that easy to make sure that, for example, you have different spin than all your neighbors because you have so many neighbors. And it turns out that actually there is a pretty straightforward way of mapping any problem from, like maybe not any problem, but like a lot of combinatorial optimization problems from kind of mathematical representation to an Ising Hamiltonian. So a quick example how to do that for MaxCat. So in case of MaxCat, you have CA and CB. CA and CB can be either 0 or 1, or like, sorry, let's say like -1 or +1, right? So if the node is green, then it's like +1. If the node is blue, then it's -1. So this is, so if they are both the same, right? So it's like 1 times 1 or minus times -1, then you don't want to put this into the cost function. It should be 0 because you don't care about edges that go between, that go between the nodes in the same group. But if there are different, you get -1 here. So we have -1, -1, -2. So this kind of goes into your cost function. Actually, this is lacking some coefficients, and perhaps it will give you like the solution with the minus sign, but kind of these are details that I don't want to bother you with. But the thing is that you can very easily map this into Ising Hamiltonian by simply replacing the value of the one of the nodes, right, with the operator, right? So it's Z operator acting on qubit A or qubit B. And basically then if you take a state, well, in this state, this will be kind of, if you measure it, it will be either 0 or 1, and it will allow you to kind of map this, like the measurements that you have, again, into this cost function. So that's basically how you map MaxCut into an Ising model so that you can then solve it on a quantum computer. Like another concept is that comes in handy is time evolution. So at the top, you can see time-independent Schrödinger equation, which basically says, so we want to know, how the change, so how the state changes in time if we act on that with a Hamiltonian H. And the solution to that problem is pretty straightforward, which is that, it changes as if we acted on the state, starting state with such operator for the time t. So what I want for you to take from this is that whenever you see something which looks like e to the power of minus something times h, like times Hamiltonian, this means that we probably deal with some kind of evolution, and the parameters roughly correspond to for how long you were operating, you were like using this operator to act on a quantum state. Because it's like allows to get some better intuition than just like looking at it and saying, oh, well, this is like some operator, and I don't know why it has this like special form. Okay, the next thing is function approximation. So in the classical world, we can have some mathematical expression, and then we can approximate it by, taking its values for like many different x's, right? So if we have 1,000 points, then our approximation is pretty smooth and nice. If we lower the number of points, then the approximation gets, worse and worse. So, it's kind of pretty easy to understand how it's happening in the kind of classical world. The problem is when we try to, let's say we have a Hamiltonian, which is like super hard to kind of put it on the quantum circuit for like whatever the reason. And we want to approximate the Hamiltonian. So, how can we do that? And how can we do that in such way that we have control over, like how many points basically we have, right? Because, obviously the number of like 1,000 points, the approximation is much better, but you actually had to calculate the value of this function 1,000 times, right? And if, and then 15 points actually is not that much worse, and you only had to evaluate your cost function only 15 times, right? So, there are trade-offs. And for example, we would like to be able to kind of adjust like how many times we need to, like how good approximation we really need. So then the concept of trotterization comes. And yeah, I know, like, sorry for just like throwing these equations at you, but basically what it says is that we have an operator of this form, so e to the power of a plus b, then we can simulate it by just putting for n times this like alternating operator. So it's like a, b, like e to the a, e to the b, e to the a, e to the b, like divided by some constant, right? And even better, like if we want like some higher order approximation, there is also this expression. So I want, for what I want to remember is like that we have this like alternating kind of operators. And also another thing that's useful is that we can approximate an operator acting for time from t0 to t by, you know, having some other operators acting from like sometimes. And this is like piecewise linear approximations, right? Because in here you see that, well, this is linear function, this is linear function, this is linear function, this is linear function, and they're just like acting from x equal -5 to x equals something, and so on and so on. So we can similarly kind of approximate our whole operator by like having this small pieces that are, you know, kind of easier. Okay, so that was a lot. But now we have kind of all the pieces that allow us to understand what's QAOA and why it looks the way it is. So QAOA basically prepares this state that we denote as like gamma beta, which consists of the kind of some initial state S, right? So we start from the state, and we then apply an operator U of C and gamma 1, and then U of B and beta 1, and then U of C and gamma 2, and U of B and beta 2, and up to some P. So basically, like how many times we apply this is called sometimes steps, and it's like usually denoted by P, right? So does it resemble something? At this point it should, because we have this alternating operator as we had in trotterization. And if you take a look actually at how U of C and U of B like look like, okay, I'll get, okay, you will see like how it ties even better into trotterization. But first, how does it tie into adiabatic quantum computing? So basically, it looks like approximating something. So if we wanted to do kind of simulate adiabatic computing, we could take like trotterization of this Hamiltonian that's like linear combination, right? And just like trotterize it with like very, very kind of granular way. But you know, it will probably get something like this, right? But you know, it requires a lot of steps, and as I mentioned, quantum computers today are not, you know, that good at running for very long. So what we do at QAOA, we kind of try to find some shortcuts, right? So we simulate roughly the adiabatic path, but we actually don't really care if we follow it exactly. We just care to get to the point. But so this is it. And another thing is, what are these operators? So the operators look like this. So this is U of C and gamma, and it has the form of e to the power of -I gamma C, which consists of like kind of all the smaller c's. And the c are actually those terms, right, that we discussed before. In the case of MaxCat, they look something like this, right? So for each kind of pair of nodes jk, you create an operator which looks like this, and then you create a sum of that, which then the sum, when you have exponent, translates to multiplication, and you have multiplication of all these operators. Well, why it's important? I mean, what's like important here is that we have again like operator of the form e to the power of something times some Hamiltonian, right? Because C is called cost Hamiltonian. So this is basically what we do is we act on a quantum state for the time gamma with the operator C. That's like how can you read this? But we also had U of B, and for U of B we have this beta and the B Hamiltonian. And the B Hamiltonian can be many things, but in this kind of original QAOA setup, it was just a set of sigma x acting on all the qubits, right? So what we do is if we look back at the kind of QAOA, we act with the operator C, then with the B, then with the C, then with the B, then with the B, C and the B, and so on and so on. Okay, why would we do that? Because you know, one question that I had and I struggled with understanding is, okay, I have this cost Hamiltonian which encodes my problem. So why don't I just apply it to the quantum system, which like should guide me into the direction of the solution? Why do I even need this mixer Hamiltonian? Well, the reason for that is that we need mixer Hamiltonian because if we didn't have it, we would kind of got stuck in the first eigenstate of C that we would encounter, which probably would not be the ground state. So basically what mixer Hamiltonian does, so we apply I thought about this metaphor, like, you know, being a forest full of traps, right? So you kind of don't want to go anywhere, and you know kind of in what direction the treasure is. So we always try to go into the direction of the treasure. But at the same time, you kind of cannot just go straight to the treasure because there are a lot of traps. So you need to know how to avoid them, right? And the traps are kind of local minima in this case. So what you do is you like cost Hamiltonian kind of guides you towards the optimum, and mixer Hamiltonian kind of allows you to avoid these traps along the way, right? And tells you kind of where you can step. So what makes a good mixer Hamiltonian? Well, it needs to be easy to implement because, you know, you don't want to have like million of gates, even if it, you know, if it might have some merit, but it will be hard to run it. And it has to be something that doesn't commute with the cost Hamiltonian, because if it did commute it with cost Hamiltonian, then once you get into some eigen values, you will eigenstates, you will not be able to escape it. Okay, so let's now see an example of QAOA problem. So we have this graph with 3 nodes, 0, 1, 2, and the values of the edges is like 10, 10, and 1. So we want to construct a cost Hamiltonian, right? So, well, for the 0 and 1, we have the constant term of like 1/2, which is like always there. Then we have coefficients, so like 10, because the weight between them is 10. And then we have this 1 minus sigma 0, sigma, like sigma z0, sigma z1. So before I had z1, now I have the sigmas. This is basically the same, like different ways of denoting the poly Z matrix. Sorry for like not keeping the notation kind of the same. So what happens if both of them are 1, right? If both of these qubits, we measure both of them to be let's say 0, the energy of this will translate to 1. So we have times 1 times 1, right? So if they are both 1, they're like kind of in the same group, so we don't need to count them. If they are different, so one is 1 and the other is -1, then we get 1 minus 1 times -1, so 1 plus 1, so it's 2. So we get that the cost of like kind of interaction between these 2 nodes is 10. And then we do basically the same thing with all the other. Well, with the exception that for 1 and 2, this edge has the cost 1, so we don't have this 10 multiplier. Okay, and now we know how the Hamiltonian looks like, and we can write, you know, all those e to the power of minus I gamma HC. But actually, how do we translate this into a circuit? So, well, this is something I will not cover because it's like that will be too much. But basically, there exists a method of translating this translating this like exponentiated Hamiltonians into a circuit. So if we do that, then the circuit looks something like this. So we have a layer of Hadamard gates, right, which create the equal superposition, which is our initial state. Then we have this. This comes from IBM. These are like some fancy gates, but they are basically, you can think about like 2-qubit gate and 1-qubit gate. You can implement this each of like these blocks with like different sets of gates, but you see that there is this interaction here that has this -10, this interaction here that has this -10, and this one has -1, and they correspond to like, you know, different terms of the Hamiltonian, right? And also you can see that here we have 5, and this 5 comes from the fact that we said that the gamma should be equal to 0.5, and this gets multiplied by like 10, and here it doesn't get multiplied by 10. So I mean, I know what I'm saying right now is pretty vague, but what I want to show is that the structure of the QAOA circuit is basically like taking each of these Hamiltonian terms and like putting them into like one piece like this, right? For the mixer Hamiltonian, we have a layer of Rx, so rotation around x-axis, with these values, which correspond to the beta angle, right? And then we do measurements. And then we also have like outside optimization loop, which allows us to find the good parameters of beta and gamma. Okay, so before we go into like second round of questions, I would like to tell you about the relationship between VQE and QAOA. So in principle, like QAOA, you can look at it as a special case of VQE, but with kind of very, very specific ansatz, right? Given that the ansatz is always consists only of the Z matrices, it doesn't have any X or Y terms, you can drop this whole like kind of measurement, rotating to measure in the right basis. But so this is like one difference, but there are like some other like differences. And I think as I said, like the ansatz form is limited. You're restricted to Ising Hamiltonians, which also kind of allows you to save some time on these rotations. But in principle, I think that the most important difference is that actually the goal of these two methods is very different, because in case of VQE, we care about finding the ground state energy and maybe also finding the ground state, right? So you need to have produce, like with your ansatz, you need to produce a quantum state which has like very, very high overlap with the ground state. So perfectly, it will be like the ground state. But in QAOA, you actually don't, because what you really care about in QAOA is finding a bit string which is a solution to your problem. And actually, you know, you can get into the exact ground state, and this will be perfect, but you also don't really need to do that, because you might also find a state which has, let's say, 20% overlap with the ground state. And in such case, you will have a state which gives you the right result 20% of time. So if you measure your circuit, you will get the right bit string 20 out of, you know, like 20% of time. And you don't really need any more, because if you can say that, you know, this is the best bit string I got, this is basically the solution to your problem. So you don't need to really produce a state which gives you 100% overlap with your ground state. You only need high enough overlap so that you get the solution to your problem. Okay, so let's see some QAOA questions. Okay, I'll go through the chat.
Yeah, there were some answers to the previous question about the measurements only possible in Z basis.
Yeah. So I see a good question from Satya. In classical ML, we usually get stuck in local minima because the optimization functions are normally non-convex. What happens for such Hamiltonians with DQA? Well, we have the same problem basically. I mean, depending on the Hamiltonian, but there are some Hamiltonians that are like easier, some that are harder, but that's more or less the same problem. The Ising model would be useful in two-dimensional space, like 2DG gas. I have no idea. Where do weights of the edges in the max cut problem appear in the Hamiltonian? So Wojtek, I hope I answered this question already. What is the, if not, please ask kind of more refined version. What's the 1/2 coefficient for roughly? Okay, so the 1/2 coefficient is just for, if we take a look here, if you take here, so if you have, this comes from like this equation. So let's say you have, so this equation is for the graph where all the edges have coefficient 1, so we don't have coefficient. So if we have 1 times 1, we get 0, right? But if we have minus 1 times 1, we get -1. So it's -1, -1, so we get 2. But actually, you want to have 1. So you just divide it by 1/2. So it's like, I mean, it's important if you don't have this 1/2 coefficient, then you will basically get the value of the cost function, which is twice as big as the one you wanted to get, which like still is like linear scaling, so it's not a huge deal, but it's better to have this 2 over there. Sorry, I'm trying to look. Okay, chat. Okay, so yes, the good by Satya, trotterization can be applied to any Hamiltonian. That's true. That's true. I showed that in the context of QAOA just like only. So you managed to solve kind of graph coloring with 2 colors. No, MaxCut is not graph coloring really. This is like separate problem. You can also map graph coloring, because in graph coloring problem you don't really care what are the weights between the different nodes. In graph coloring you care only so that the colors, the nodes of the same color don't touch each other, right? So these are like two distinct problems, but you can also map a graph coloring problem on an Ising Hamiltonian and then use QAOA to solve it. Okay, so we don't have like kind of a lot of time, I guess. It's already been a lot, but fortunately this part from now on is a little bit kind of lighter, I hope. So I would like to tell you a little bit about challenges of the NISQ and why actually we care about variational quantum algorithms for near-term devices, and then try to generalize some concepts that we talked about to show you how kind of they can apply it like basically any variational quantum algorithm. Okay, so the challenges of the NISQ era are these are probably the most important ones. There are probably many others. So as I said, noise. So you can never kind of be sure whether the operation that you applied is, the one that you wanted to apply. So you try to keep the number of operations as short as possible. So then the lifetime of qubits. So basically this is due to decoherence. So after some time qubits will kind of collapse to the 0 state. So you only know you can use them for only as long. Then number of qubits. So, well, we have devices with limited number of qubits. So in principle, we can deal with the noise by doing error corrections, but for error correction, you need a lot of additional qubits. And we have like 50 qubits on like at most right now, and not like 1 million qubits. So we want to have algorithms that could work also with hundreds of qubits and not millions. As I already mentioned at some point, well, you don't necessarily have all the gates available on specific hardware. So, you know, it's sometimes tricky to translate your circuit from, for example, CNOTs and Pauli operators to like rotation around XYZ to the hardware which doesn't have CNOT but has something else. So it like adds additional overhead. And you don't want to have overhead for the reasons already mentioned. And also you cannot connect all qubits all to each other. So if you take a look at this, like this graph here, so let's say we have a linear chip, right? So qubit 0 is connected to qubit 1 and qubit 1 to qubit 2, but there is no connection between qubit 2 and qubit 0. So everything works pretty well except this gate here. So actually, in such case, you need to kind of make some tricks, like, I don't know, for example, use a swap gate to kind of be able to perform these operations because these two qubits don't lie next to each other. And, well, how these issues affect us. So here are some plots from Google's paper about QAOA. So just to give you some idea of where we are with QAOA right now, on the left plot, you can see that, well, the P is the number of steps of QAOA, right? And basically, this is the kind of mean cost function, and this is how many samples were kind of good ones, right? So we see that it peaks around 2 or 3, and you know this is for like actually relatively simple case. So in theory, the more layers of QAOA you add, the kind of better results you get. But when you account for the noise and like some other effects, actually you cannot apply too many because then you get worse and worse results, right? So, you know, right now we are, and also like some other experimental implementations show this, that right now with current quantum devices, we are around P = 3. And another issue is that if you don't have deep enough ansatz, then your expressibility is low, right? Because, you know, it's just like sometimes some problems with like one layer, you can't really find the optimal solution to this problem because your ansatz kind of will never reach the state, the ground state. So some problems are simply not solvable with like such small numbers of P's, and well, we're just here right now. And the other thing is the effect of noise. So what you see in this plot is kind of the shape of the cost function, right? So basically, the higher the lighter the better. And these are like for kind of 3 different types of graphs, and these are beta and gamma values. So as you can see in the noiseless simulations, they all look nice and symmetrical. But as we go to the experiment, it actually turns out that, well, we have a lot of kind of glitches here. And, you know, the dark isn't as dark as it should be, and the bright isn't as bright as it should be. So in this case, like the SK model at the bottom, you see that, well, this minimum is actually not even like well reflected here. I mean, it's super easy to kind of miss it, right? So this is kind of the stuff that we are dealing with right now. And no, it's just good to have that context and to see why, you know, doing VQA is hard. But why actually they are good for the NISQ devices, even though of these like issues I told you? Well, the one thing is that they usually allow for variable circuit depth. So in QAOA, you know, once we get better hardware, we can just start putting, you know, more and more layers, right? Now we have not as good hardware, so we are stuck at 3 layers. But in a couple of years, we'll be able to get more and more layers. And that's not necessarily the case with some kind of more classical quantum algorithms, where you don't have this trade-off. You either, you know, apply all the operations or you won't get the right result. Here, you know, this is heuristic algorithm and you have some control over that. They actually show some resistance to noise. So, you know, even though we have some noise in these pictures here, well, we are still able to find actually the right solution to this problem. So, you know, that's quite nice. And there are like some other reasons why, there are like some other experiments that show that actually VQE and QAOA are like somewhat resistant to noise. And well, they don't necessarily need a lot of qubits. So in some algorithms like I don't know, like Grover or Shor, you sometimes need like thousands of qubits or millions of qubits to actually make them work. And in VQA, well, you also need, you know, some qubits, but it seems that with hundreds of qubits, you will already be able to like get some interesting calculations done. Okay, so the last thing I wanted to talk about is the structure of variational quantum algorithms. So kind of the way to generalize it a little bit. So let's say we want to implement like some quantum algorithm. So we take a circuit, we run it on QVM or QPU. So QVM is a simulator, QPU is like quantum processing unit, a real chip. And then we get some measurements, right? Right. Seems, I mean, pretty straightforward. That's how you do quantum computing. Well, but, you know, as I already mentioned a couple of times, what about the chip layout, right? Maybe not all qubits are connected. And what about the gate set? Maybe we don't have all the gates. So, well, we need to add the compiler, right? So we have this abstract circuit that's in whatever gates we kind of want. Then we add compiler, which transforms all this into a circuit which is actually executable on our hardware, and then we run simulation or on real hardware. We get some measurements and we are happy, right? And we use like some QPU specs as input to the compiler because, you know, it needs to know on what chip we want to run it. Well, that's great, but actually, you know, haven't we spent a lot of time talking about ansatz and, you know, some other issues that are also here? So how do we, you know, account for that? So ansatz, we already know what ansatz is. It definitely not in this picture. Readout correction. So basically, when you run stuff on hardware, you're able to sometimes to say that, well, these measurements are definitely bad, and you have different ways of doing like this readout correction. So and like discard or like correct some of the measurements. So this is something that also would be nice to have. And they're like the whole thing of measurement strategy. So, you know, when we look at the hydrogen example, you might have seen that, well, we have this one term acting on Z0, the other term acting on Z1, and the other on Z3, and the other on like Z4. I mean, not acting on, like having Pauli Z gate acting on qubit 0 to 4. So we don't really need to run a separate circuit for like each of them. They are all independent of each other. So we can run one circuit and measure all the 4 qubits at the same time, and voila. But that's not, you know, in some cases it's super easy, but in some other cases, actually the way you group those terms in the Hamiltonian so that you can measure them together is extremely tricky. So it's like very active area of research. How do you group them? And also like Schotz allocation. So perhaps you have this one term which has coefficient of like 10 to the minus 5. And you have this other coefficient that has the value of other term with coefficient like 100, right? So obviously the second one is much more important than the first one. So you probably want to spend kind of, if you have like 1 million, you know, you are able to do 1 million measurements, you probably want to like have more measurements for this term which has higher coefficient, right? And actually strategies for doing that are also pretty elaborate, and that's like another thing. And also, like, if you want to make a simulation and make it reliable and like reflecting reality better, you need to have some noise models, which is also tricky. So you have to like add this to your picture. Okay, so we start from some ansatz, right? Based on this ansatz, we create some abstract circuit, and based on ansatz and parameters, right? Then we compile it, have executable circuit. Then we can run it on QVM and QPU. But if we are running simulations, we actually want to use some noise models. If we run on hardware, perhaps we want to use some readout correction. And then, as I said, we might want to add some measurement strategies to that, and then we get measurement. So we can actually divide this picture into two parts. So one is more about like circuit preparation, and then execution and measurement. But hey, we forgot to talk about classical optimization loop, right? So, well, so two things. So one is like problem definition, but what if our problem has, you know, some constraints, right? Or what if we want to use some different cost function than simply averaging the like the one that I showed you, like the most basic ones, like taking the Hamiltonians, like averaging the energy. And if we want to have some bounds on the parameters, for example, in QAOA, the cost, like the landscape is periodic in gamma and beta, so there is no need to, you know, have allowing for gamma and beta to be from 0 to like 10,000. It's just like enough to be like from 0 to 2 pi or 0 to pi, depending on the case. So, you know, you want to add this into your algorithm, but also we have the optimizer, and you need to choose which optimizer do you use. Is it regular gradient descent, or maybe it's like a non-gradient method like Nelder-Mead, or maybe LBFDS or Adam or something else. You need to choose parameters like of the algorithm, right? So like the step size, for example, or if it's like gradient descent with momentum, then it's momentum, or, you know, like a lot of parameters to choose from. Then you need to find some initial parameters that are, you know, it's better to start from good initial parameters rather than bad ones. And there's like a whole field of like, what's actually a good way of calculating gradients? There are like many ways, like someone in the chat mentioned natural gradients. So yeah, you can use natural gradients, you can use finite differences, you can use like some other methods, parameter shift through, for example, and, you know, it actually gets complicated pretty fast. So this is how this picture looks like when you try to account for all that, right? So you have, here is what we had in the previous diagram. So circuit preparation and like execution measurements, but actually we need to have good problem definition. We need to have some parameter initialization strategy. After we measure, we pass parameters to the optimizer, and so on, right? So it's all like, once you start, it looks like pretty simple at the beginning, but like once you start digging, it's get more and more complicated. And I bet like you can take any of these boxes, open it, and there will be like a lot of stuff to actually create it even more complicated. So this is like, you know, I try to kind of make it more systematic. So like this diagram works similarly for, like it's probably the same roughly for VQE, QAOA, and perhaps even QNNs. But, you know, it also illustrates like how complicated these algorithms really are. So briefly at the end, so some challenges of variational quantum algorithms are, well, ansatz design. So, well, how do you design ansatz which meets all the criteria we talked about? And, you know, it's not easy. How do you perform optimization? There are like many issues. So for example, one is barren plateaus. So it turns out that actually for gradient-based optimizers, it might be very hard to optimize these parameterizable circuits because there are a lot of space in the optimization landscape where the gradient is like close to 0. So optimizer will like just go crazy or like don't move at all. Or like just choosing the right optimization method and choosing like the right method for calculating gradients is huge. Measurement problem. So, well, this is something that if you do your math, and if you want, for example, to calculate the ground state energy with VQE with high enough precision, it might turn out that you need like billions of measurements, like, you know, in every iteration. So it turns out that actually, even though, you know, it seems that it might be a reasonable algorithm, the runtimes might be really, really crazy, and we need to find some ways of actually decreasing number of measurements that we need. And like we recently had a paper from Zapata that explores it, but you know, it's a huge problem. Another thing is that there are honestly like, you know, provable speedups for these methods. So we kind of have reasons to think they will work, but it's not that we can say, okay, so like using VQE will give us exponential speed up over like existing traditional methods. Well, we can't say that. Like it's too complicated to be like for us to be able to make such statements. And they're like all the various possible improvements. So what I mean by this is like stuff that I have even not shown in that picture. How to benchmark them, you know, a lot for example, for QAOA, a lot of papers that come out are focused on solving QAOA for MaxCut, but you know, perhaps on like 3 regular graphs usually, but you know, it's not very practical, honestly. And I mean, in the sense that this problem is not that hard to solve with classical computer, and you know, it's not clear whether, you know, this is a good problem to benchmark this algorithm, or maybe there are like some other problems to benchmark it that are better. The same goes for VQE. There are like a lot of open questions, how to make this benchmark like fair. Well, it's just like, you know, hard to say. And also there's like simulation versus experiment. So you might have a method which works pretty well in simulation, but then when you run experiment, you know, you have seen what experiment can make with your can do with your optimization landscape. So there are a lot of also like kind of friction on that front. So with that kind of optimistic optimistic outlook on the challenges of VQA, I would like to like quickly summarize what we went through. So I've explained to you how VQE works and why it works, how QAOA works and like why it should work. Why do we think that these are good algorithms for the NISQ era? And also I went through like some more generic structure of variational quantum algorithms. So thank you very much for the attention. You can find me in the internet on my blog. I strongly recommend kind of going through VQE and QAOA blog posts, and there will be more to come. And also you can find me on Twitter with this handle. And now I'm open to questions.
Right, thank you very much, Michał, very nice lecture. Yes, indeed, let's try to answer several more questions. There's a question from Alberto Acuto, a question about application to quantum machine learning versus NISQ. It has been pointed out that the basic idea of quantum computing is surprisingly similar to that of kernel methods in machine learning. There has been some suggestions that variational methods for QML are in principle better suited for near-term devices, while kernel methods, for instance, those leading to, for example, QSVM, provide a theoretical research framework that is more long-breathed to suit a post-NISQ scenario in a better way. What's your opinion regarding this?
Okay, so that's pretty involved question, I would say. So, well, my opinion in short is I don't know. So I'm not that I'm not like that up to date with QML research. It's like there is a lot happening there. Mm-hmm. I think that, well, it's pretty important to tackle these problems both kind of from the short term and like long term perspective. And it's actually it's not that easy, like, you know, to say which methods which pieces are actually very long term and which are more like short term, because it might turn out that like some of the methods that we develop for fault tolerant quantum computers are actually, with slight modifications, might be usable like much sooner than we thought, and vice versa. Like some methods that we come up for like those NISQ devices might actually be also applicable for the long term. I would say that regarding these questions, I would look into the research by Maria Schult. She is like an excellent researcher in the field of QML. If you, yeah, like if anyone's interested, you can find me in the internet, and I can probably provide with some literature on the topic, but I don't really have like a strong opinion.
Okay.
So right now it seems that adiabatic computing is more powerful than QAOA. Would you agree? So, well, I kind of wouldn't. And the reason I wouldn't agree with that is, no, like QAOA is, why I think like QAOA is more powerful than adiabatic computing is that QAOA is here today and we can do this, and adiabatic computing, well, it's not that much. I mean, I guess there are some experiments which are doing this, but I think it's like in principle, you can simulate adiabatic computing with QAOA. So in some sense, if you can have like infinite number of steps, you can basically replicate adiabatic computing with QAOA. So in some sense, they're like kind of equal, but QAOA in the short term gives you, like allows you to like cheat a little bit, let's say, on the kind of adiabatic path and just get to the result faster. It's like, I guess it's like more flexible than adiabatic computing. But yeah, I mean, I think that's it.
Yeah, there is a link from Vladimir Korepin regarding optimization of Grover search. So thank you, Vladimir, for that. And there is a question of from Samit. How do different measurement strategies affect the results?
Well, different measurement strategies affect the result differently. So I would say it's, I mean, it's pretty, I mean, like pretty broad question. So let's take one particular, like as an example. So, and like, I think measurement strategy is pretty also like broad thing. I'm not sure whether it's like well defined what is the measurement strategy, what's not, like, because I don't know even if like grouping strategies are measurement strategies, or like that people actually say that these are two different things. But like, let's say with grouping, so if you do no grouping, okay, I will go back to the hydrogen example. Okay, so in this case, if you do no grouping, you have to run the circuit for each of this term, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So you have to run the circuit 15 times. And like each time you probably need to run it like 1,000 times to get some good, like, you know, number of samples. So it's like 15,000 times. If you group these together, you can definitely, I mean, okay, you don't need to run for the identity term ever, so it's like 14,000. If you group these four together, and you can't do that because they are all totally independent, then it reduces it from 14,000 runs to 11,000 runs, right? If furthermore you group Z0, Z1 with Z2, Z3, that is like 1,000 measurements less, then you can also probably pair Z0, Z2 with Z1, Z3, and Z0, Z3 with Z1, Z2. There's like 3,000 less measurements. So in total, it's 3 here, 3 here, so it's 6. So it's like from 14,000 measurements, we got into 8,000 measurements just by like very simple grouping. So, well, this is one of the kind of examples how grouping strategies can affect the results, right? And also, you know, if, as I kind of already pointed out, if you want to play with shots allocation, oh, actually, this is like pretty interesting thought that I have. I'm not sure if anyone actually tried doing this, but if you know about like some example where someone tried doing it, I would be happy to learn that. So actually, it turns out that this is done with like these landscapes are created with pretty probably large number of samples, but you don't really need to have like 1 million samples to see that this point, black point here, is much worse than this bright point here, right? You probably can distinguish that with, I don't know, like let's say like 1,000 samples, right? So probably like in the initial phase of optimization, you can use lower number of samples to just kind of get the idea where you want to get. And once you start approaching the actually optimal, like the minimum, then the difference between this pixel here and this pixel here is so little that you probably need more, like more measurements than like this, let's say 1,000, right? So another like kind of measurement strategy that one might want to use is like having smaller number of measurements at the beginning of optimization, and then like higher number of measurements when you start converging. And well, if you do that, you like save a lot of measurements at the beginning. So that's like how this strategy might affect the results. You can basically get the same results, but like in shorter time and with smaller number of measurements.
Okay, great, thanks. The next question from Devanshi Arora: how to determine the number of shots of the quantum algorithm be determined to get less errors in the algorithm to run on quantum device?
I think I don't know of any like kind of good method. I guess, well, one way is to just run it and see how it works. And I guess this is kind of the most like foolproof method, because you just kind of will see how it really works, and it's like not very complicated. But I guess there are also probably some like simple statistical facts, like the fact that if you have, well, I don't remember the details, but I think if you have sample from like a Gaussian distribution, then the kind of the precision of your evaluation. So sorry, it's like hard for me to say like to frame it, but basically the more precision you want to get, the more measurements you need, and the relation is quadratic, right? So you need, if you want to have if you want to go from, I don't know, the precision of 0.1 to 0.01, you don't need 10 times as many measurements, you need 100 more measurements, right? Or something like this. So basically there's like some, some threshold over which it doesn't make sense to, make more measurements, because the gain that you have is like so small.
Right. Okay. I've also pasted a link to the lecture of Maria Schult. So Michał mentioned Maria Schult in the context of quantum machine learning, if someone is interested. There is also one more question about, yeah, super. It's not very relevant to the topic of the lecture, I guess, but let's ask. Superconducting qubits versus trapped ions versus photonics. Which one of the implementation approaches you think will most likely get us to the promised land first?
Well, it's pure speculation, I think, like from my end, because I'm not kind of hardware person, so I don't know enough to make any kind of good claims. Like they all have like different pros and cons. So for example, in case of like what I talked about, well, superconducting has limited conductivity, right? But they usually run faster. And trapped ions have better connectivity, because in principle you can have like all-to-all connectivity, so it makes some problems much easier to solve. but you know, the amount of time you need to run the circuit is like, I don't know, like about 10 times longer, I think. So there are trade-offs everywhere, and it's really hard to say which of, you know, characteristic will turn out to be the most important, and hard to say.
Okay, thanks. We don't have more questions on our chat. Michał, do you still have time so that I can ask one or two more questions?
Yeah, sure.
Okay. So you mentioned that QAOA and variational quantum algorithms were one of the most important algorithms in the last decade in quantum computing. How do you think, what might be the future? So do you think that those variational methods will be also similarly important in the future, or are you aware of some interesting research directions? Are there some interesting variants of those algorithms which are especially promising?
So I would say that it's a good question, and I would say that, well, you know, no one knows what the future will bring, but variational quantum algorithms are still very unexplored, and we still really don't understand very well a lot of things that are happening. And once we start moving with the hardware from, you know, the stuff that we can simulate classically to the things that we can run only on hardware, it will also probably will see some, you know, kind of new problems, but maybe also new hopes. And I think that, you know, it might be the case like someone will come up with some great idea,
okay,
you know, tomorrow, but I think the variational quantum algorithms will probably still be pretty important in the upcoming years. And regarding improvements, well, there are a lot of improvements, and they are very, you know, many of them are very kind of incremental. So sometimes there are like just so many variants of like, for example, QAOA and the way so you can run it. And I think that the basic principles kind of, so mostly what I was talking about today will probably stay the same, but probably some elements will change dramatically. So yeah, so like one thing I can think about is the estimation of the expectation values, which is like as I mentioned, like there was this recent paper by Zapata, and it's just like it's using like Bayesian inference to calculate the expectation values, and it's really very kind of novel and powerful method, and perhaps, you know, it will also like change the way we look at the circuits, and maybe inspire someone to like come up with some new methods. But yeah, it's like speculation.
Okay, so one more question. You said that QAOA might be especially, or is especially useful for solving combinatorial optimization problems. Are you aware of any applications beside combinatorial optimization? So I know that many problems which are apparently not combinatorial optimization can be also transformed to combinatorial optimization, but in many cases it's just not efficient, and it's not reasonable to do that.
Yeah.
So are there is there maybe, or are there any families of problems, sub-problems for which QAOA might be especially successful?
So I'm not aware of any like right away. Like an example is, I mean, it's like, it's hard to say, you know, where the boundary lies, but for example, there's this paper by guys from ProteinCure where they used QAOA to, you know, help with protein solving, because you can frame some problems. So protein solving, I mean protein folding. You can frame some problems in protein folding as combinatorial optimization problems, but that's still a combinatorial optimization. One thing that comes to my mind is Max Henderson from Rigetti was talking that for quantum neural networks, so like for some quantum machine learning basically use cases, they used QAOA ansatz as one of the layers of the neural networks. And it might turn out that, that might be like some kind of area that might be interesting. So like using QAOA ansatz not QAOA as like the whole algorithm, but just like taking the ansatz and reusing it in some other methods. So, well, it gave them better results than the approach they tried earlier. And I think it's like interesting direction, but I think like the QAOA is mostly focused on combinatorial optimization problems right now.
Okay, great, thanks. So maybe last question. Can you tell us maybe a bit more what exactly are you doing now in Zapata Computing and Quantum Open Source Foundation? If it's
sure. Sure. So at Zapata, we are building Orchestra, as I said, which is like the platform which allows you to do quantum computing. It's not like, so it's like a workflow management system that helps running experiments. It's not like another library like Qiskit or Cirq. It's like more kind of much higher level. And one of the things I've been working on for the last couple of months is writing the Python code for like the scientific part. You can check it out on the Zapata's GitHub. So basically kind of designing these libraries in a way that it's like very easy to swap, for example, different optimizers or different ansatzes, right? Or different backends, so that you can have this very modular code that allows you to easily compare different methods. So like you keep all the variables like the same, except for using different optimizer or using different grouping strategy or using different ansatz and so on. And it turns out to be surprisingly difficult task to like create this architecture. I've been talking about it in a recent talk, so I'm not sure if the video is already publicly available, but if anyone is interested, you can, once it will be, I will publish it on my blog. And if not, you can ping me wherever, and I will send me an email, and I will give you the link. And at Quantum Open Source Foundation, so we have finished the mentorship program. So the first, we were running for the last couple of months program for people interested in quantum computing, that we paired them with mentors, which are either from industry and academia, and they've worked for like 3 or 4 months on the project. And we just finished it. We published, and all the projects are open source. You can find it on qosf.org/qcmentorship. And right now we'll be working on preparing for the second batch of the mentorship program, which will probably start in fall. And yeah, I mean, there are some other initiatives going on in QOSF, but that's the one that I was mostly working on myself.
Okay, I see that there was a question from Devanshi exactly about quantum computing mentorship program. So I think that you already answered this question. And yep. Also there's a question about internships, virtual internships at Zapata.
You can apply, and I don't know, like we have a couple of interns right now. I'm not sure, I'm not like involved in hiring. So I don't know what are our plans regarding getting more interns, but you can always, I think there's like open position for internships, so you can apply and see what happens.
All right.
So I need to go.
Okay, and that was the last question, so from my side at least. Thank you very much, Michał, once again. It was a really great talk, interesting, and I also would like to thank all the participants for also very interesting questions. As I said, the video recording will be available soon on our YouTube channel, so stay tuned. Please follow our channels, join our Facebook group. And the next meeting of Warsaw Quantum Computing Group will be probably in October, so we have now a summer break in Poland, holidays, so we'll start again our meetings in October, so also stay tuned.